totally different partition on the interval CV up into subintervals. And I need to argue, and it's sort of not obvious exactly how to do this, that I can somehow fuse these two partitions together or define some new partition, which is kind of like the concatenation of these two partitions or something, and then sort of stitch it back together into one big integral. Somehow that a good partition followed by another good partition is like still good, to use my vocab. It doesn't seem too hard, but it's not exactly so easy either. So we'll just leave it. Okay, here's another one. I think I can squeeze this on here without erasing. Property 5. Okay, what's the integral from a to a of some function? Okay, well, this is maybe just silly, and you might want to say the answer is just 0, and you are right. I got 3 arguments for you. 1, the technical one. Well, if delta x has been defined, so to speak, at least on equal width subintervals, as b minus a over n, well, in this case, the upper limit of integration is a, and the lower limit of integration is also a, over n. And so in this case, it's sort of like my delta x is 0. And so if I were just to interpret this literally, using the definition, which should work, then this would be the limit as n approaches infinity of the Riemann sum, the sum from I equals 1 to n, of f of x sub I star, times, but now you just have like a minus a over n, and that's just 0. So in this case, delta x is just 0, and so this is just all just 0, and you're just summing up a bunch of zeros, man. I mean, this is just the sum f of x sub I star times 0. And if you add up a bunch of zeros, then that's just 0. So this is just 0. Okay, so technical sort of proof. Then there's the geometric interpretation, which is basically pretty silly. Here's a, here's my f function, but it's just kind of like I don't go anywhere. You're finding the area of a rectangle with no width to it. So that's pretty clear. And then the physics interpretation is that you have some velocity function, but your time interval is just 0. Okay. So good. That's 3 arguments for that. All right, 2 more. Maybe I'll just do 1 more even. I've already gone over. It's too long. Isn't it too long? Okay, so 2 more. This one is maybe the one that's most difficult to understand intuitively, and our textbook just doesn't even try. This is the integral from 6 to 2. So if we're taking the integral from 6 to 2, say, this is my example, of some function, how am I supposed to understand this? You might even object that like this is just sort of like not allowed, right? In fact, haven't we called this the lower limit of integration, and the one on the top is the upper limit of integration? Doesn't this number have to be smaller? Well, I don't know. Does it? I claim no, and if you just do the problem, what do you see? So okay, let's just do it. This would be the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I star times delta x. And what's delta x? Delta x is always just b minus a over n. In other words, like I was saying a second ago, it's the upper limit of integration minus the lower limit of integration over the number of subintervals. But, okay, here, what happens when you do this? You get that b is 2 and a is 6. And so what we find here is, is you get f of x sub I star, and then delta x is like negative. And how am I supposed to understand this this negative delta x? Or maybe we're not even doing understanding it. Maybe we're just trusting that this is what a Riemann sum is. It's a product of a bunch of functions times a bunch of widths. But maybe the width can be negative, or at least here it just is. But I think now we sort of know what to do, and the what to do is that I can just factor this negative out of the summation and also just out of the limit. So this becomes negative, the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I star 4 over n. So just get that negative out of there. Okay, but now we have the same function, but now the subintervals, the widths are back to being positive again. Okay, so this is just sort of by definition negative the integral from 2 to 6. Okay, and so this maybe explains, well, I don't think this explains. This demonstrates that as long as you interpret this delta x literally as that number minus that number, then this integral from 6 to 2 is in fact just the negative of the integral from 2 to 6. How can we sort of understand this geometrically? Well, I think that's possible. We have some, so here's 1, 2, 3, 4, 5, 6. So here's 2, here's 6. So I'll draw the function sort of the normal way or something. But now I have these backwards rectangles. This is not a technical term, but it is a learning term. What is a backwards rectangle? A backwards rectangle is a rectangle which counts negatively toward your Riemann sum. Not as like what happened in the previous videos, because the function happens to be negative there, but because the width is negative. In fact, even if the function is positive, as I've drawn it, I have this sort of negative rectangle, or I have a rectangle which is contributing negatively to the Riemann sum, I guess is the way to put it. So this is this delta x is negative 4 over n. And so what you have to imagine, and this gets kind of casual and maybe you find it kind of weird, but if I'm integrating from 6 to 2, then in some crucial sense I'm integrating backwards. And if I'm integrating backwards from 6 to 2, then my entire partition is such that I sort of begin over here and move kind of that way in my partition. And if I'm moving that way in my partition, then all my changes in x are all going to be negative. If I do equal width subintervals, in fact, they'll all be negative 4 over n. And so I'm multiplying at every stage the height of the function by the amount I just shifted by, and the amount I've just shifted by is always negative. And so that sort of explains, that was my attempt at a geometry proof of this fact, that if you integrate sort of backwards, so to speak, from 6 to 2, then what you're going to get is what we would normally call the area under the curve, but the negative of that. And that's exactly what this says here. And finally, the physics interpretation. This one is maybe the most tricky of all. I have some positive velocity, so I have some sort of object which is moving forward or moving to the right from time 2 to time 6. But by asking about the integral from 6 to 2, I'm sort of asking, okay, so the integral from 2 to 6 would answer the question, what was the change in position from time 2 to time 6? And in this case, the change in position from time 2 to time 6 would be positive, because this velocity is positive, so we're moving to the right, and so positive displacement happens. But the integral from 6 to 2 would answer the question, what is the displacement from time 6 to time 2? So somehow you're running the clock backwards. You're imagining sort of time going backwards, or the independent variable sort of going backwards. And from time 6 to time 2, we in fact do experience a negative displacement, if that makes some kind of sense. Okay, the general principle, here maybe the geometry and the physics is confusing, but the Riemann sum is telling you like it is. And in fact, the more general rule is that regardless of whether a and b, which is bigger, the integral from a to b of some function is always going to be the opposite of the integral from b to a. And it's sort of customary in these situations to just like flip it to make it go the right way. Okay, I'll stop there. Goodbye.